On January 9th, 1857, at 8:13 in the morning, a magnitude 6 earthquake struck the Parkfield section of the San Andreas fault. 11 minutes later, 360 kilometers of California ground tore open. The Carrizo Plain section ruptured. The towns of Fort Tejon collapsed. The dust at the rupture, by contemporary accounts, blocked the sun. It was the largest earthquake in California's recorded history, and the only thing that gave it 11 minutes of warning was a small Parkfield earthquake that, in modern terminology, dynamically triggered the main shock. Tonight, May 19th, 2026, the Parkfield segment is 21 years and 7 months past its most recent characteristic earthquake. Its mean recurrence interval is 22 years. The Carrizo Plain section south of it has been silent for 169 years, the longest documented quiet on that segment in 6 centuries. And in the 7 days leading to tonight, 6 different structures across the western US Pacific plate boundary lit up at the same time. The configuration is the closest analogue to 1857 that has ever been documented. So the question that hangs over tonight is simple. Both clocks have run out. The strain has been building since the Civil War, and the same trigger pathway that started the 1857 sequence is, by every measurement we can make, currently in place. What does that actually mean? Before we go any further, if you enjoy what we do here at Project Nightwatch, hit like and subscribe so you don't miss any of our nightly debriefs. Drop a comment and tell me where you're watching from tonight. Let's get into it. Part 1. The Parkfield segment and what it has been doing for 169 years. There is a stretch of California ground, about 25 miles long, that has been doing something the rest of the San Andreas fault has not done in living memory. It has been keeping time. Not the kind of time you measure with a clock on a wall, the kind of time that the planet itself seems to count, in events spaced almost exactly the same distance apart, century after century, like a metronome buried under the dirt. And that stretch of ground, that little segment of fault running through the dry yellow hills of central California, is called Parkfield. If you have never heard the name before, that is fine. Most people have not. There is a town there. There is a one-room schoolhouse. There is a single cafe where the menus joke about being on the fault that moves, and the locals serve you breakfast on a counter that has, at points in the last century, physically slid sideways while customers were eating. And there is, beneath it all, a piece of the most studied tectonic boundary on Earth that has produced a magnitude 6 earthquake roughly every 22 years for as long as we have records of it doing so. The last time it did was September 28th, 2004. As of tonight, that was 21 years, 7 months, and 21 days ago. By every numerical measure of its own history, the segment is now sitting right at its mean recurrence interval. The clock has run out. And that is not the most interesting part of this story. The most interesting part is what sits directly south of Parkfield. Because south of Parkfield, the San Andreas changes character. It stops creeping. It locks. It enters what geologists call the Carrizo Plain section, and then the Big Bend, and then the long, slow southward sweep down toward Cajun Pass. And along that locked section, the most recent rupture happened on a January morning in 1857. It was a magnitude 7.9. It tore the ground open for 360 kilometers. It produced surface offsets where one side of the fault slid past the other by 9.5 meters in a few seconds. It was the largest earthquake in California's recorded history, and the only thing comparable to it before that was a rupture in approximately 1690, and before that, in approximately 1490. The mean interval between major Carrizo Plain ruptures, by every published estimate, is somewhere between roughly 88 and 168 years. As of tonight, the interval since 1857 is 169 years, 4 months, and 10 days, the longest documented gap on that segment since at least the 15th century. We are, by the metrics of the segment's own paleoseismic record, in territory that none of us alive has seen. And those two facts, the Parkfield clock sitting at its mean and the Carrizo Plain quiet sitting at its maximum, would on their own be the story. That alone is what you came here for. But there is a third element that makes this particular night worth the 2 hours of your life you're about to give it. And that third element is what was actually happening underneath California in the 7 days leading up to right now. Because in those 7 days, 6 different structural domains of the Western Pacific plate boundary lit up at the same time. The Parkfield segment itself produced a cluster of small earthquakes with a southward propagating signature that one open-source seismologist watching the data live on Monday morning described, in his exact words, as the fault trying to unzip its way down south. The Salton Trough at the other end of California produced a swarm of 347 small events. The San Jacinto Fault Zone in Imperial County produced a sub-swarm of 40 earthquakes overnight. The Mendocino Triple Junction, up at the northern end of California, produced a magnitude 5.3. The Cascadia Subduction Zone produced an active count of 16 slow-slip tremor events along its southern margin. And way out in Nevada, the Fallon Swarm, which has now been running for over 30 days, kicked up again. 6 structures. The Pacific Plate's entire western boundary, expressing stress signals on the same day, in a configuration that, when you lay it next to the documented signature of what was happening in California in early 1857, looks almost identical. That is not a forecast. Let me say that clearly, because I am going to say it again at the end of this video, and you should hear it now too. That is not a forecast. Nobody, including the United States Geological Survey, can tell you whether something is about to happen this week, or this month, or this year. The history of trying to predict the Parkfield earthquake is, as you will hear later in this video, the history of being wrong about exactly that. But what this stretch of California ground is doing right now, is a documented climatological position that we can describe precisely. The clock is at its mean. The magazine south of the clock has been silent for 169 years, and the rest of the western US Pacific Plate boundary is humming. That is the configuration. And the only other time in the last 600 years of paleoseismic record that we have anything resembling this configuration, the result was 1857. So tonight, what we are going to do is walk through this very carefully. I am not going to tell you something bad is about to happen. I am going to tell you what the data are. I am going to tell you what the historical precedent is. I am going to tell you what the most studied fault segment on Earth has actually taught us about prediction, both its failures and its successes. And I'm going to tell you by the end of this video what the honest interpretation of where we are right now actually sounds like. Because I think you have been sold the wrong story about California earthquakes for most of your life. The story you have been sold is mostly about Los Angeles, about the urban San Andreas at Wrightwood and the Kagan Pass and the suburbs of San Bernardino, about when the big one is finally going to hit. And there is a real version of that story, and we will tell some of it. But the actual scientific story, the one that the data tonight are pointing at, is about a quiet stretch of ranch land halfway between San Francisco and Los Angeles that almost nobody outside of seismology can find on a map. It is about a town of 18 people and a cafe that jokes about the fault that moves. And it is about a small magnitude 3.2 that struck on Monday morning, May 18th, 2026, near a place called Kettleman City, immediately east of the Parkfield segment, on a secondary structure rather than the San Andreas itself. The event was not on the San Andreas, but it was right next to it. And in the language of crustal mechanics, that location is what is called a stress transfer pathway. Movement on a secondary structure relieves, or accumulates, stress on the primary structure beside it. And the secondary structure east of Parkfield has, for at least 3 decades of measurement, been documented as a pressure gauge for what the Parkfield segment is doing. A 3.2 on that secondary structure is a small event, but a small event there, paired with the southward unzipping pattern on the Parkfield segment itself, paired with the simultaneous activity across the western boundary, is what the open source monitoring tradition in California now flags, not as a forecast, as a configuration. The reason I want to start the video here, before getting into the history and the prediction experiment and the 1857 rupture in detail, is that I want you to understand from the very first words what the editorial premise of this video actually is. It is not that something is about to happen. It is that the structural setup that preceded one of the worst earthquakes in California's recorded history is currently being more closely replicated than it has been at any point in modern instrumental record. That is a documented fact. You can argue about what it means. You can argue about whether it carries predictive weight. You can argue about whether the simultaneity of the western boundary signals is causal or coincidental, but you cannot argue that the configuration is not present. It is present, and the science of why that matters is the actual story. So let us start at the beginning. Let us start with Parkfield. 25 miles of fault in the dry yellow hills between Coalinga and Cholame, on a stretch of road most Californians have driven past without stopping, on land where the cattle outnumber the people, on a creek that flows for 3 months a year and then dries up to dust, on a segment of the planet that, every 22 years on average, decides to move. The geography of Parkfield itself is part of why the segment matters scientifically, and it's worth spending a moment on the physical setting before we get to the prediction experiment. The town sits in a narrow valley at an elevation of about 1,500 feet, between the Diablo Range to the west and the Temblor Range to the east, in Monterey County, California. The San Andreas Fault runs almost due northwest-southeast through the valley, and the surface trace is visible from the air as a continuous lineament, running through grassland and across small creeks. The town itself consists of, at last census, a population of 18 people, served by a post office, a one-room schoolhouse that doubles as a community centre, a single cafe that serves the Parkfield ranching community, and the small number of tourists and scientists who pass through, and the V6 Ranch, which has been owned by the same family for several generations, and which sits on land that has been physically translated sideways along the San Andreas by repeated characteristic earthquakes throughout its history. The Cholum Valley, just south of Parkfield, is similarly sparsely populated, and is best known to most Californians for being the location where the actor James Dean was killed in a traffic accident in 1955 on a stretch of state highway that crosses the San Andreas Fault about a mile from the location of the eventual 2004 Parkfield rupture. The geographic obscurity of Parkfield is part of what made it suitable as a research site. There were no large urban populations to disrupt with the instrumentation effort. There was no significant commercial activity to require permits and right-of-way arrangements. The land was, by US standards, almost empty. The fault, by US standards, was almost full. Why, you might reasonably ask, does this specific segment produce characteristic earthquakes when the rest of the San Andreas does not seem to follow the same pattern? The answer is in the structural geology of the segment. North of Parkfield, the San Andreas creeps. That is the technical term for the behaviour. The fault slides past itself slowly and continuously, at a rate of a few millimetres to a few centimetres per year, without producing significant earthquakes. The slip is released aseismically, in the same way that a slowly leaking pipe releases water without producing a sudden burst. South of Parkfield, the fault locks. The two sides of the fault stick to each other. The relative plate motion has to go somewhere. The strain accumulates over decades or centuries, and the eventual release comes in the form of a major earthquake. The Parkfield segment itself sits at the transition between the creeping and locked sections. It is the boundary, and at that boundary the behaviour is intermediate. The segment locks for a period, accumulates strain, releases it in a magnitude 6 characteristic earthquake, and then begins the cycle again. The 22-year mean interval is the empirical signature of that intermediate behaviour. It is a transitional regime, neither fully creeping nor fully locked, that produces a distinctive recurrence pattern not seen elsewhere on the San Andreas system. Part 2. The most studied fault segment on Earth. In 1985, the United States Geological Survey did something it had never done before and has not done since with anything like the same level of public commitment. It made a prediction, not a forecast, a prediction, a specific falsifiable deadline-attached claim about a future earthquake, written down in a peer-reviewed journal, attached to a budget and announced to the press. The prediction was this: there would be a magnitude 6 earthquake on the Parkfield segment of the San Andreas Fault on or before January 1st, 1993. The probability of this happening, the USGS said, was 95%. The mechanism for that prediction was straightforward. The Parkfield segment had by then produced documented magnitude 6 events in 1857, 1881, 1901, 1922, 1934 and 1966. 6 events over 109 years. The mean interval between them was approximately 22 years. The last one had been in 1966. 22 years after 1966 was 1988. Build in some uncertainty on either side, and you arrive at a window that closes in 1993. That was the prediction. To make it falsifiable, the USGS did the most ambitious instrumentation project in the history of seismology. They sent technicians to Parkfield with crates of equipment. They drilled boreholes for strain meters. They strung cables across creeks. They set up creep meters along the surface trace of the fault. devices that look like little white boxes with rods running into the ground, designed to record millimeter-scale sideways movement of the fault on a continuous basis. They installed continuous GPS stations back when GPS was still primarily a military technology, and the civilian receivers were the size of a backpack. They installed magnetometers because there was a hypothesis at the time, going back to work in the Soviet Union, that earthquakes might produce measurable magnetic field anomalies as their nucleation zones approached failure. They put water level sensors down wells, because there was another hypothesis that the pore pressure changes preceding a rupture might be detectable in groundwater. They built what is now called the High-Resolution Seismic Network, an array of seismometers buried in shallow boreholes around the Parkfield segment, designed to record micro-earthquakes down to magnitudes of around 0, which is to say, ground motion so small that a person standing directly on top of them would feel nothing at all. They wired all of this up, they started recording, and then they waited, and 1988 came, and nothing happened, and 1990 came, and nothing happened, and 1993 came, the deadline of the original prediction, and nothing happened. The Parkfield segment, which had been moving every 22 years for 109 years, simply refused to do its scheduled thing. Editorials started getting written. Some seismologists, particularly outside the United States, started saying out loud that the experiment had failed, and that the implication was that the characteristic earthquake hypothesis itself was wrong. That maybe the apparent 22-year periodicity was an artifact of an undersampled record. That maybe the Parkfield earthquakes were not in fact characteristic at all, but simply random events that had happened to fall in a sequence that looked patterned to human eyes. That maybe earthquake prediction was a fundamentally unworkable scientific project, and the whole enterprise should be retired. For 19 years after the original deadline, the experiment continued. The USGS kept the instruments running. They kept publishing the data. They quietly walked back the original prediction in 2002, in a release that stated that the 5-year probability of a characteristic Parkfield event was no longer elevated above background. They had conceded. And then on September 28, 2004, at 10 minutes past 5 in the afternoon Pacific time, the magnitude 6 occurred. The Parkfield characteristic earthquake, the one that had been predicted for 1988, finally arrived. It was 16 years late. It nucleated approximately 10 kilometers from the location the original prediction had placed it. It ruptured to the southeast rather than the northwest, the opposite of the direction the historical sequence had suggested. And because the instrumented array had been running continuously for 19 years by then, it recorded the entire event in the most extraordinary detail any earthquake had ever been recorded. The borehole strain meters captured the stress build-up in the seconds before rupture. The seismometers captured the nucleation phase in micro detail. The GPS stations captured the surface deformation in real time. The creep meters captured the surface slip. The magnetometers captured the magnetic field changes. The water level sensors captured the pore pressure response. Every instrument they had installed captured something, and what they captured was in many ways more important than the earthquake itself. What they captured was that even on the most instrumented fault segment on Earth, even with 28 different categories of sensor running continuously for 19 years, even with the densest array of seismic and geodetic instrumentation ever deployed on a single fault, even with the entire resources of the United States Geological Survey focused on this 125-mile stretch of dirt, the earthquake produced no clear short-term precursors. There was no anomalous strain signal in the days before. There was no detectable magnetic field anomaly. There was no clear water level change. There was no foreshock sequence on the hours-to-days timescale that could have triggered a warning. The earthquake arrived, the way earthquakes mostly arrive, without telling anyone it was coming. This was the moment in which modern earthquake science had to make peace with itself. The 2004 Parkfield event simultaneously validated and invalidated the characteristic earthquake hypothesis. It validated it in the sense that, eventually, the magnitude 6 event arrived, in approximately the right location, with approximately the right magnitude. The long-term recurrence-based forecasting did work, in the sense that the event the historical sequence implied would eventually arrive did eventually arrive. The pattern was real. But it also invalidated the deterministic prediction premise. The exact location was off by 10 kilometers, the direction was wrong, the timing was 16 years late, and the instrumented precursors, the whole reason for the experiment, were not there. The implications of this rippled across the entire field of earthquake science. In the years immediately following the 2004 event, several major published reviews of the experiment grappled with what it meant for the prospects of earthquake prediction in general. The consensus that emerged, articulated in a special issue of the Bulletin of the Seismological Society of America in 2006, was approximately the following. The Parkfield experiment had been the best test case anyone could design. The segment had been the densest instrumented in the world. The historical record had been the clearest and most periodic in the world. The funding had been adequate. The personnel had been the most experienced. And under all of those favourable conditions, deterministic short-term prediction had failed. If it could not be made to work at Parkfield, it could not be made to work anywhere. The science of earthquake prediction, as a project distinct from the science of long-term hazard forecasting and short-term early warning, was effectively over. That conclusion has held up in the 20 years since. There has been no major new short-term prediction research initiative in the United States since 2004. The funding has gone instead to hazard mapping, to early warning systems like Shake Alert, and to fundamental research on the physics of rupture. Prediction in the deterministic sense. The prediction that says an earthquake of approximately this magnitude will happen at approximately this location at approximately this time is, in the consensus view of the modern field, not a tractable scientific project. The Parkfield experiment is why. That historical context matters tonight because it changes how you should interpret the configuration that this video is describing. If we were living in a scientific era where short-term prediction was a credible enterprise, then the configuration would arguably support some kind of prediction statement. We are not living in that era. We are living in the era in which the most ambitious prediction attempt in human history failed in instructive ways, and in which the responsible position is to describe configurations rather than to predict events. That is the position this video takes. The configuration is what it is. The interpretation of what to do about it is, for each viewer, a personal and household decision about preparation, about risk tolerance, and about long-term planning in a region that the published hazard literature has identified as carrying real and persistent seismic risk. So the lesson of Parkfield, the actual published lesson that the seismological community drew from the 1985 to 2004 experiment, is the lesson that we should be carrying into every conversation about California earthquake hazard today. The lesson is this. Long-term recurrence-based forecasting on this specific segment has empirical support. The events do happen with a mean interval that is real within a range of variance that is real, but the short-term nucleation point, the rupture direction, and the timing within the climatological window are not deterministically predictable from prior events. The data does not have that resolution. The science does not have that resolution. Nobody knows when, within the recurrence window, the next event will arrive, and nobody, including the people watching this video, including me, will be able to tell you a date. That distinction matters, because the rest of this video, the part where we are going to walk through where the Parkfield clock sits today, where the Carrizo Plain section sits, what happened this week on the western US plate boundary, what the 1857 sequence actually looked like, all of it sits inside this distinction. The configuration is real, the clock is real, the historical analogue is real, but the short-term timing is not knowable, and anyone telling you they know is selling you something. The USGS has never been able to tell you. The most instrumented fault segment on Earth could not be made to tell anyone, and that in itself is one of the most important pieces of information you can carry forward. What the experiment did succeed at, though, was establishing that the recurrence-based long-term forecasting was empirically valid for at least this one segment. Parkfield, on a multi-decade timescale, does produce magnitude 6 characteristic earthquakes at intervals averaging 22 years. The 2004 event was the 7th in a documented sequence going back to 1857. The mathematical record is now this: 1857, 1881, 1901, 1922, 1934, 1966, 2004. The intervals between them are, in order, 24 years, 20 years, 21 years, 12 years, 32 years, and 38 years. The straight average of those 6 intervals is exactly 24.5 years. If you weight the more recent events differently, or if you exclude the 1934 event as a partial rupture rather than a full characteristic event, the average drops to around 22 years. Either way, the climatological window is somewhere in the low 20s. As of tonight, 21.6 years have passed since 2004. The window is open. The mean has been reached. The most studied fault segment on Earth is currently doing exactly what its historical record predicts it should be doing, which is sitting there, accumulating stress, waiting. Whether it produces its characteristic earthquake tomorrow, next month, next year, or in 2034, the science cannot tell you. The window is the window, and the window is open. And while the window is open at Parkfield, the segment immediately south of Parkfield, the segment that uses Parkfield as its northern terminus, the segment that ruptured in 1857 and has been silent since, is also doing exactly what its historical record predicts it should be doing. It is sitting there accumulating stress, exceeding every published recurrence interval estimate on what is now the longest documented quiet in its paleoseismic record since at least the 15th century. The clock at Parkfield is at its mean. The magazine south of it is past every documented threshold. So that is where we are. That is the configuration. That is the editorial premise of the rest of this video. Now we need to walk through what specifically that configuration looked like in 1857, because the 1857 sequence is the empirical precedent for what happens when both of those clocks are running out at the same time. Part 3. September 28th, 2004. When the clock finally caught up. The morning of September 28th, 2004 was clear and warm in central California. The fields around Parkfield were dry. It was the end of summer. The cattle were where the cattle had been all season. The instruments on the segment were running, as they had been running every day since 1985, recording the small movements of the Earth that nobody outside of the USGS data archive ever pays attention to. At 10 minutes past 5 o'clock in the afternoon, local time, that changed. What happened in the seconds before the rupture was something that no instrument had ever previously captured at this level of detail. The borehole strain meters, devices that measure the deformation of solid rock at a depth of several hundred meters below the surface, recorded a small but detectable acceleration of strain in the final seconds before the fault failed. That was not predicted. The published assumption going into the experiment had been that strain would accumulate at a steady rate, and then, at some unpredictable moment, release. Instead, what the strain meters recorded was that strain accelerated in the last few seconds. Not enough time for any warning to be useful, but enough time, in the post-event analysis, to suggest that there was a small detectable signature in the very final phase of nucleation. The high-resolution seismic network, the array of buried seismometers, recorded a small foreshock approximately 1 second before the main rupture, at almost exactly the same location. The water level sensors recorded a small pre-rupture decrease in well water levels in the seconds immediately before the event, consistent with crustal dilatancy, which is a fancy way of saying the rock fractured open just slightly before the main slip released the accumulated stress. These were, in the language of post-event analysis, real precursors. They were detectable. They had been detected. The catch was that they happened in the final 1 to 10 seconds before the rupture. Not the days, not the hours, the seconds. By the time any of these signals could be confirmed, processed, or relayed, the earthquake was already in progress. The seismograms from the dense array show the rupture nucleated at a depth of about 7.9 kilometers, near a feature on the segment that subsequent reanalysis identified as a structural asperity, a region of locally high friction that had been accumulating stress for the previous 38 years. The rupture propagated southeast, away from the predicted nucleation point, at a speed of approximately 3 kilometers per second for about 15 kilometers before terminating. Total duration of the surface rupture, from nucleation to termination, was approximately 5 seconds, magnitude 6.0 on the moment magnitude scale. Shaking was felt across central California from San Francisco to Los Angeles. There were no fatalities. There was very limited structural damage, mostly to old buildings in the immediate Parkfield area, and to highway bridges and overpasses within a few miles of the surface trace. The Parkfield Cafe, the one with the menu joking about being on the fault that moves, was reported by news photographers in the days after the event to have a fresh crack down one wall. That was the local damage. There was no further significant aftershock larger than about magnitude 5. So what did the experiment learn? What it learned, first and most cleanly, was that the recurrence-based long-term forecast was correct. The event happened, in approximately the right location, with approximately the right magnitude, within the 20-year window of the original prediction, once you accounted for the prior 38-year interval and the variance documented across the historical record. The science of long-term recurrence-based forecasting on this specific segment is, in retrospect, considered validated. The Parkfield segment really does produce characteristic earthquakes at intervals averaging in the low 20s, with significant variance. What it learned, second, was that the deterministic short-term prediction premise was wrong. The location was off by 10 kilometers, the direction was wrong, the timing was 16 years late. The pre-event precursor instruments, designed to detect signals on the hours to days timescale, did not detect anything until the final 1 to 10 seconds, far too late for any usable warning. What it learned, third, was that there is in fact a small and possibly real precursor signal in the very final seconds of earthquake nucleation. The strain meter acceleration, the dilatancy water level drop, the 1-second foreshock, these are real. Whether they are predictive in any operationally useful sense, on faults that have not been instrumented to the same density as Parkfield, is a separate question. The answer to that question, in 2026, is still that they are not. Earthquake early warning systems like California's Shake Alert do operate, but they work by detecting the first seismic waves from an event that has already started, and providing seconds of warning before the strongest shaking arrives. That is different from prediction. That is rapid detection of an event in progress. It is useful. It can buy schoolchildren a moment to drop and cover or stop a high-speed train before the strong motion arrives. But it is not the same thing as predicting that an earthquake will occur next Tuesday afternoon. What it learned, fourth, was that the aftermath of a Parkfield characteristic event is not just the main shock. The 2004 event was followed by a substantial period of a seismic afterslip, which is to say the fault continued to slip slowly, without producing earthquakes, in the months and years after the rupture. Continuous GPS measurements showed that the cumulative aseismic slip released over the decade after the event was equivalent in seismic moment terms to a magnitude 5.8 earthquake. In other words, the Parkfield segment continued to release stress quietly long after the main rupture, in a way that no historical analysis had ever quantified. This is important for the current question of where the segment sits today, because if you include the post-2004 aseismic release in the recurrence calculation, the segment may be slightly less primed for the next characteristic event than the simple 22-year clock would suggest. This is one of the complicating considerations the modern hazard analysis takes seriously. It does not change the fact that the clock is at its mean. It does mean that the variance around that mean has additional uncertainty. What it learned, fifth, and most quietly, was that the Parkfield experiment had answered the question it was originally designed to answer, even though the answer was not the one the original designers had hoped for. The question was whether earthquakes are predictable. The answer was, mostly, not. Not on the timescales that would matter for evacuation or preparation. The data are not in the system. The instruments cannot detect what the system does not produce. The honest version of the science is that long-term hazard is forecastable, short-term timing is not, and the public should be planning on the basis of the long-term forecasts rather than expecting a warning shortly before the event. This is the place where I want to make sure I am being clear with you, because the rest of this video is about a configuration that the data, tonight, are showing us. And the temptation, when you hear the kind of pattern I'm about to walk you through, is to read it as a prediction, to hear it as me telling you something is about to happen on a specific timescale. That is not what this is. The honest position, the position the Parkfield experiment forced the seismological community to occupy, is that the long-term hazard is real, the climatological window is open, and the short-term timing is not knowable. If I knew when, I would tell you. The USGS does not know. The seismological community does not know. Nobody who's being honest with you knows. What we know is the configuration, the climatology, the analog. We will walk through all of those. But the timing of the next event, whenever it comes, will not be foreshadowed in a way that any of us will see in advance. The 2004 event taught us that. And then it taught us one more thing, which I want to leave part 3 with, because it bridges directly into the 1857 story we're going to tell in part 5. The 2004 event ruptured to the southeast. That is the direction toward the Carrizo Plain, the direction toward the locked section of the San Andreas that has been silent for 169 years. The 2004 event was small enough that the rupture stopped after about 15 kilometers and did not propagate into the Carrizo Plain section. But it ruptured in the right direction. It demonstrated empirically that Parkfield ruptures can in fact propagate southward toward the locked segment. The 1857 event, as we will see, ruptured in exactly the same direction. The difference was magnitude. The difference was how far the rupture went before it stopped. And the question that has hung over Southern California seismology since the 2004 event closed, the prediction experiment, is the question of what happens the next time a Parkfield characteristic earthquake nucleates and ruptures southward, and the Carrizo Plain segment beyond it has been silent for, by then, even longer than it had been in 1857. Not whether such an event is possible. We know it is possible. We have the 1857 precedent. The question is what the conditions for that propagation actually are, and whether they are present in 2026. Part 4, Where the Clock Sits Today, 21.6 years in. Tonight, as I am narrating this, the time elapsed since the September 28, 2004, Parkfield characteristic earthquake is 21 years, 7 months and 21 days. Expressed in decimal years, that is 21.64. The historical mean interval for Parkfield characteristic earthquakes is, depending on which average you take, somewhere between 22 years and 24.5 years. We are on the lower bound essentially at the mean. On the upper bound, we're about 2.5 years short of it. Either way, we're inside the climatological window. The clock is up. Now, climatological windows are not deadlines. The variance in the documented sequence is wide. The 12-year interval between 1922 and 1934 sat well below the mean. The 38-year interval between 1966 and 2004 sat well above it. The next event could arrive next week. It could arrive in 2034. The variance is real, and the post-2004 seismic afterslip discussed in the prior section adds some additional uncertainty by potentially shifting the recurrence window estimates slightly to the right. But however you do the math, 2026 is, by every reasonable interpretation of the historical record, inside the window. The Parkfield segment itself, on the morning of May 17th and into the morning of May 18th, 2026, did something that the open-source seismological monitoring tradition flagged in real time. A small cluster of earthquakes activated along the segment. The pattern, as described in real-time monitoring overnight on May 17th into May 18th, was a southward propagating sequence. Small events, none of them larger than around magnitude 3. But arranged in a temporal spatial pattern that, when plotted on the segment, traced out a line moving from the northwestern end of the segment toward the southeastern end. That is the same direction the 2004 event eventually ruptured. That is the same direction the 1857 event ruptured. The morning of May 18th produced the magnitude 3.2 near Kettleman City. That event was not on the San Andreas itself, as I noted earlier. It was on a secondary structure roughly 20 miles east of the Parkfield surface trace. The relevance of the Kettleman City event is the documented geodetic coupling between the secondary structures of the southern San Joaquin Valley and the Parkfield segment. The two are not independent. Activity on the secondary structures statistically correlates with stress changes on the segment. A 3.2 in that region is, in itself, a routine event that any given month produces somewhere in California. But a 3.2 in that region paired with the southward unzipping signature on the Parkfield segment proper, paired with the broader simultaneity of activity across the western boundary, is a more specific configuration than the channel-wide statistical average. That same morning, in fact, was when the open-source seismological tradition in Central California chose its language carefully. The phrase used in real time, narrating the data live as it came in, was trying to unzip its way down south. That phrase has technical content. Unzipping is the colloquial term for what seismologists call sequential rupture nucleation, in which small events accumulate along a fault line in a pattern that traces the direction of eventual main rupture propagation. The unzipping pattern, when it is present, is one of the few hours-to-days timescale signatures that has been documented in some historical pre-rupture sequences. It is not deterministic. Most unzipping patterns do not produce a main rupture, but the pattern itself is real, and when it appears on a segment that is climatologically at its recurrence mean, on top of a structure that historically has produced characteristic earthquakes, in a direction that matches the direction of historical rupture propagation, It is the kind of signal that the open source monitoring community flags. That flag, on the morning of May 18, 2026, was the editorial premise that brought you to this video tonight. Now let me anchor this back to where the segment actually sits, not in interpretive terms, in quantitative terms. The Parkfield segment has, between the historical record's first documented characteristic event in 1857 and the 2004 event, hosted 7 magnitude 6 characteristic earthquakes. The mean interval is 22 to 24 years, depending on weighting. The current interval is 21.64 years. The clock is at the mean. The Carrizo Plain segment immediately south of Parkfield has, by paleoseismic reconstruction at Wallace Creek, hosted documented major ruptures in approximately 1490, 1690 and 1857. The mean recurrence interval is, depending on which paired events you use, somewhere between 88 and 168 years. The current interval is 169 years. The clock is past the mean by every published estimate. Geodetic measurements over the past 169 years, derived from continuous GPS stations across the Southern California crust, indicate that the Carrizo Plain segment has accumulated approximately 5.9 meters of unreleased right lateral slip since the 1857 event. For reference, the 1857 event itself released approximately 9.5 meters of surface offset at Wallace Creek. The current accumulated slip deficit is therefore approximately 62% of the slip that was released in 1857. That is to say, the Carrizo Plain section currently has enough accumulated stress to release, if it ruptured today, approximately 60% of the slip that the 1857 event released. That would correspond to a rupture roughly proportional in length and magnitude, though precisely how those scaling laws map onto modern moment magnitude estimates is a matter of some quantitative debate. The order of magnitude answer is that the segment today contains enough accumulated strain energy to produce something between approximately magnitude 7.5 and magnitude 7.9, depending on how the rupture nucleates, propagates and terminates. The United States Geological Survey's most recent published probabilistic forecast for the southern San Andreas system, the Uniform California Earthquake Rupture Forecast version 3, assigns a 30-year probability of approximately 19 to 31% for a magnitude 7 or greater event on the southern San Andreas. That is not a probability of any particular week or month or year. It is a 30-year cumulative probability across the entire segment. For perspective, the same probabilistic forecast, when applied to the average California household's risk of a single major earthquake in a 30-year mortgage period, places the risk on a par with the cumulative 30-year probability of a structure fire. People do not generally consider a 30-year structure fire risk to be a reason to refuse to buy a house. They do, generally, install smoke detectors and buy insurance. The honest analogy for Southern California seismic risk is somewhere in that range. But the 30-year probability, while accurate, also obscures something. The probability is not uniform across the 30 years. The probability is conditional on what has happened in the preceding period. The first year of the 30-year window has the lowest annual probability. The 30th year has the highest, and the underlying climatology that drives those increasing annual probabilities is the same climatology that has placed us today, 169 years out from 1857, at the longest documented quiet on the Carrizo Plain segment, in approximately 6 centuries of paleoseismic record. So when we put the Parkfield clock at its mean, alongside the Carrizo Plain clock past its mean, alongside the documented southward unzipping pattern on the Parkfield segment in the last 72 hours, alongside the secondary structure event at Kettleman City paired to that segment, alongside the simultaneous activity across the rest of the western US Pacific plate boundary, what we have is a configuration that none of us alive has previously seen, but that the 1857 record describes in detail. We have the empirical analogue. We have the data of what that analogue produced. The question is what the analogue tells us and what it does not tell us about what to expect from the present configuration. To answer that, we have to walk through the 1857 sequence in actual detail. Not as a folk myth, not as a historical artifact, as what it actually was, hour by hour, on January 9th of that year. That is what Part 5 is going to do. Part 5, January 9th, 1857. How the last one actually started. The morning of January 9th, 1857 was cold and clear across central and southern California. The state had been part of the United States for less than 7 years. The non-indigenous population was sparse, perhaps 400,000 people total in the whole state, most of them in San Francisco and the Gold Country. Southern California was rancho country, with isolated settlements at Los Angeles, San Bernardino and Fort Tejon, a U.S. Army garrison in the Tejon Pass that had been established in 1854 to protect overland travel between the Central Valley and the Los Angeles Basin. The fort was the most heavily populated location in the 1857 rupture zone, which is why the earthquake came to be named for it, even though the geographic centre of the rupture was farther north. What we know about the 1857 sequence, the actual hour-by-hour progression of the morning's seismic events, comes from a combination of 3 sources. First, contemporary newspaper accounts and personal letters from witnesses across Central and Southern California. Second, the surface offset evidence preserved in the landscape, which Carrizo and his successors mapped in detail starting in the 1970s and continuing to the present. Third, the paleoseismic trench studies at Pallet Creek, Wrightwood and Wallace Creek, which placed the 1857 event within the longer documented history of major ruptures on the segment. What the combined sources tell us is this. At approximately 8:13 in the morning, local time, on January 9th, 1857, a magnitude approximately 6 event occurred on or near the Parkfield segment of the San Andreas. It was felt at Fort Tejon, approximately 70 miles to the southeast. It was felt in the small settlement at Cholame. It was felt in the Central Valley. The intensity, by modern reconstruction, was consistent with a magnitude in the 6 to 6.5 range, with a rupture located on the Parkfield segment, propagating to the southeast, the same direction the 2004 event would eventually propagate. This was the foreshock, or more precisely, this was a magnitude 6 characteristic Parkfield earthquake that, in modern terminology, dynamically triggered what followed 11 minutes later. At approximately 8:24 in the morning, the southeastern terminus of the Parkfield rupture reached, or passed, the structural transition into the Carrizo Plain section, and at that moment, the Carrizo Plain segment, which had been locked since approximately 1690, ruptured. The main shock began. From the southeastern end of the Parkfield segment, the rupture front propagated southeastward at approximately 3 to 4 kilometers per second into the locked section. It crossed the Carrizo Plain, it crossed the Cholame Valley, it crossed the Fraser Mountain section, it reached the Tejon Pass, it crossed the southern Big Bend, and it terminated near Tejon Pass, approximately 360 kilometers from where the Parkfield trigger had nucleated 11 minutes earlier. At Wallace Creek, the surface offset measured by modern survey is approximately 9.5 meters. That is the cumulative displacement between the 2 sides of the fault produced by the rupture, in the matter of a few tens of seconds as the rupture front passed that location. 9.5 meters. 1 block of California physically slid past the adjacent block by 9.5 meters. That is the documented signature of the 1857 event at its center point. To put 9.5 meters in human terms, that is roughly the length of a school bus. The 1857 event displaced the 2 sides of the fault, at Wallace Creek, by approximately the length of a school bus, in a matter of tens of seconds. Imagine standing on a road that crosses the fault. Imagine watching the road that goes off to your west, on the Pacific Plate side, suddenly translate northward by approximately the length of a school bus. The road on the other side of the fault, the road that goes off to your east on the North American Plate side, stays where it is. The eastern half of the road is now offset from the western half by approximately the length of a school bus. That is what 9.5 meters of right lateral surface displacement looks like in the human-scale landscape. At Wallace Creek today, the offset stream channel that records the 1857 event is plainly visible to anyone walking the surface trace. The creek bed enters the fault zone from one direction, jogs sideways for approximately 9.5 meters along the fault, and then resumes its previous course on the other side. That jog is the earthquake. It has been preserved, almost unchanged, for 169 years, because the climate is dry and the landscape erodes slowly. The jog is, in a sense, the most direct physical signature of the 1857 event still preserved on the modern California landscape. The shaking duration, at Fort Tejon, was approximately 1 to 3 minutes. Adobe structures collapsed across the Tejon Pass Tehachapi-Fraser mountain corridor. The fort itself was damaged, with several buildings rendered unusable. Reports from Los Angeles, then a town of approximately 4,000 people, indicated that buildings cracked, walls fell, and trees shook violently for an extended period. The Los Angeles River reportedly sloshed out of its banks. The dust raised by the shaking at Fort Tejon was said to have obscured the sun. In San Francisco, 300 miles north of the rupture, chandeliers swayed and church bells rang from the long-period surface waves travelling up the coast. There was, as far as documented contemporary records can establish, one fatality. A woman in an adobe structure collapse in Southern California at the moment of the strongest shaking. The very low fatality count was a function of the very sparse population, not the moderate intensity of the shaking. Modern simulations of an equivalent rupture applied to the present-day population and built environment of Southern California project hundreds of billions of dollars in damage and tens of thousands of casualties, with infrastructure failures including bridge collapses, urban water system ruptures, freeway closures, and electrical grid outages lasting weeks. The 1857 event on its own physical merits was a magnitude 7.9. The reason it was not a catastrophe is that there was almost nothing in its path to destroy. That is not the present-day condition. But the structural detail that matters for tonight's video is not the destruction. The structural detail that matters is the sequence. The 1857 main shock did not arrive without warning. It arrived with 11 minutes of warning in the form of the Parkfield segment foreshock. The Parkfield event by itself was a magnitude 6 characteristic earthquake of the kind we have now documented repeatedly on that segment. It was the kind of event that today would produce a small amount of local damage, would be reported on the news as a significant Central California earthquake, would not cause widespread alarm beyond the immediate area, and would, in the standard narrative framing, be treated as a discrete event. It would not, in 2026, in the standard mainstream framing, be treated as a possible foreshock to a vastly larger event. That is the structural lesson of 1857. The Parkfield characteristic earthquake was the trigger. The Carrizo Plain rupture was the consequence, and the time between trigger and consequence was 11 minutes. This is the part of the historical record that the modern seismological literature treats with considerable care, because it has implications for how Southern California's emergency preparedness, communication systems, and shake alert architecture would or would not function in an analogous event today. If the next Parkfield characteristic earthquake, whenever it comes, were to dynamically trigger the Carrizo Plain segment in the way the 1857 event did, then the available warning time between the initial 6 and the subsequent 7.9 would be on the order of minutes, not hours, not days, minutes. The shake alert system would detect the initial 6, broadcast the alert across Central and Southern California, and provide several tens of seconds of warning before the strongest shaking from the larger rupture arrived at the locations most distant from the fault. That is the functional limit of what early warning technology can do in this scenario. The question that has hung over Southern California seismic hazard since the 2004 Parkfield event closed the prediction experiment is the question of whether the next Parkfield characteristic earthquake will, in fact, replicate the dynamic triggering pathway of 1857. The answer to that question depends on the stress state of the Carrizo Plain segment at the moment of the Parkfield rupture, and the stress state of the Carrizo Plain segment in 2026 is at the longest documented quiet in its paleoseismic record in approximately 600 years. The geometric and modelling work that has tried to answer this question, work by Lozos in 2016, work by Kyriakopoulos and colleagues in 2019, work by the Modern Uniform California Earthquake Rupture Forecast Project, converges on a narrow conclusion. The conclusion is that southward rupture propagation from a Parkfield characteristic event into the Carrizo Plain segment is geometrically permitted by the modern understanding of the segment transition, but is sensitive to assumed friction parameters and the precise stress state of the locked segment, neither of which can be directly measured. The modelling does not say it will happen. The modelling says it could happen, under stress states that may or may not be present, with friction parameters that can be reasonably assumed to fall within ranges where the propagation is plausible. In other words, the modelling community, working from the best available data and the best available physical models, places the dynamic triggering scenario in a probability range that is small but non-zero, and that increases as the Carrizo Plain segment continues to accumulate strain in the absence of a major rupture. The current strain accumulation, at 5.9 meters, is on the same order as the slip released in 1857. The segment is, by every reasonable measure of strain energy, in a configuration where the modelling work places the dynamic triggering probability as plausibly higher than it has been at any point since the 1857 event itself. That is, I want to emphasise again, not a forecast. It is a statement about the configuration of the system. The clocks are aligned, the strain is loaded, the historical analogue is documented, the modelling work places the propagation pathway as physically permitted. Whether the propagation pathway will be activated in any specific future Parkfield event is a question that cannot be answered with the data available. What can be said, and what I am saying in this video, is that the configuration is now closer to the 1857 configuration than it has been at any point in the modern instrumental record, and the climatological windows on both segments are open. We're about to walk through, in part 6, what the rupture itself actually did across 360 kilometers of California ground. Because the geographic specifics of the 1857 rupture matter to the editorial frame of where the modern population sits in relation to where the locked segment is and what an equivalent rupture today would cross before it terminated. The rupture in 1857 crossed terrain that, in 2026, contains the homes of approximately 10 million people. That is the physical scale of what we are talking about geographically. We will get to that in the next section. Part 6. The 360-kilometre rupture that followed. The Parkfield trigger had nucleated, the foreshock had been felt, and 11 minutes later, the southeastern end of the Parkfield rupture reached the structural transition into the Carrizo Plain segment. What followed, from the moment of that transition through the next 60 to 90 seconds of seismic time, was the longest single fault rupture in California's documented history. The Carrizo Plain is a basin sitting between the Temblor Range to the east and the Caliente Range to the west, in what is today San Luis Obispo County. The San Andreas fault crosses this plain in a series of long, straight surface lineaments visible from the air for tens of miles. Wallace Creek, the most studied paleoseismic site on the segment, sits in the middle of the plain. The fault is, at this location, almost perfectly vertical, almost perfectly straight, and produces, in major events, offsets that can be measured in single event units of several meters of right lateral slip. The 1857 event at Wallace Creek produced approximately 9.5 meters of single event offset. One side of the fault slid past the other by 9.5 meters. The duration of that single event offset at any given point along the rupture front was probably between 5 and 15 seconds. Imagine standing on one side of the fault, watching the other side slide horizontally past you by 9.5 meters in the time it takes to take a breath. That is what 1857 did at Wallace Creek. From Wallace Creek, the rupture front continued southeastward into the Cholem Valley, into the Carrizo Plain south end, and onto the Fraser Mountain section. At Fraser Mountain, the fault begins to curve. This is the start of what is called the Big Bend, the geometric feature where the San Andreas changes course from a more north-south orientation in central California to a more east-west orientation in southern California. The Big Bend is the most complex geometric feature on the San Andreas system, and its mechanics have been the subject of substantial published modelling work because the bend itself acts as a brake on rupture propagation. Stress builds up in the bend. Slip rates change across the bend. The deeper structure of the fault in the bend is geometrically complex, and major ruptures must either propagate through the bend, terminate at the bend, or jump from the bend to an adjacent fault system. In 1857, the rupture propagated through the Big Bend. It continued through the bend into the southern San Andreas across what is today Antelope Valley, and reached the vicinity of Tejon Pass, where the rupture terminated near the modern boundary between San Bernardino County and Los Angeles County. The total surface rupture length was approximately 360 kilometers. The average surface offset across the rupture was approximately 3 to 5 meters, with a peak of 9.5 meters at Wallace Creek and gradual decreases toward the rupture termini. What this rupture would do in the modern landscape, if it were to be replicated today, is the substance of the published Southern California seismic hazard work, and it is worth walking through. The northern end of the rupture, in the Parkfield Cholem area, is sparsely populated ranch land. There are no major cities within 50 miles. The structural damage, at the rupture origin, would be limited to small communities and to ranch infrastructure. Then the rupture would cross into the Carrizo Plain proper, which is still sparsely populated. Then it would reach Fraser Mountain, where the surface trace runs through national forest land and the small communities of Lake of the Woods and Fraser Park. Then it would cross the Tejon Pass section, where Interstate 5 climbs out of the Central Valley toward the Los Angeles Basin. The Tejon Pass is one of the most heavily trafficked freight corridors in the United States, and a rupture across the pass would sever the connection between the Central Valley agricultural region and the Los Angeles port complex. Damage to bridges and to the pass infrastructure itself, in a magnitude 7.9 rupture, would be expected to render the corridor unusable for an extended period, with the duration of the closure depending on the specific damage to specific bridges and the available alternative routing. From Tejon Pass, the rupture in 1857 proceeded south through the Antelope Valley and into the western edge of the San Bernardino Mountains, terminating near Tejon Pass. The Antelope Valley is today the home of approximately 300,000 people, with the cities of Palmdale and Lancaster sitting essentially on the surface trace. Tejon Pass is where Interstate 15 crosses from the high desert into the Los Angeles Basin, and it carries another substantial fraction of the western United States freight movement. The pass also carries the major water aqueduct that brings Colorado River water into Southern California, and the major electrical power transmission lines connecting the desert generation facilities to the urban load centers. A rupture across Tejon Pass, of the kind 1857 produced, would simultaneously sever the freight corridor, the water supply, and the power transmission infrastructure for substantial portions of the urban Southern California population. The infrastructural concentration at Tejon Pass is, in the published Southern California hazard literature, sometimes called the choke point. 3 of the major freight rail lines that bring goods from the Los Angeles port complex to the rest of the United States cross the San Andreas at the pass. 2 of the major water aqueducts that bring water to the Los Angeles Basin from the Colorado River and the California State Water Project cross at the pass. Multiple major power transmission lines cross. The natural gas trunk lines from the desert generation facilities cross. The fiber optic cables carrying internet traffic between Southern California and the rest of the country cross. Every major lifeline that connects the Los Angeles Basin to the rest of the United States, with the exception of the coastal road and rail corridor and certain coastal undersea cables, crosses the San Andreas at or near Tejon Pass. A rupture across the pass severs all of those connections simultaneously, and the recovery time for any individual lifeline is on the order of weeks to years depending on the specific damage. The published shakeout scenario work models multiple cascading failure pathways through this concentration of infrastructure, and the conclusions about modern recovery times reflect the difficulty of restoring all of these lifelines in parallel after a major rupture. This is the part of the modern Southern California hazard picture that is in some sense more important than the shaking damage itself. The shaking, even in a magnitude 7.9, would be survivable for the substantial majority of the affected population. Buildings constructed to modern seismic codes are designed to remain standing in shaking of this magnitude, even if they sustain significant damage. The casualty estimates from the published modelling work, while substantial in absolute numbers, are several orders of magnitude lower than the historical equivalents from comparable earthquakes in less prepared regions. The lifeline damage, however, is where modern Southern California is genuinely vulnerable. The urban water supply runs through pipes that cross the fault. The electricity grid runs through transmission lines that cross the fault. The freight system runs through bridges and overpasses that may not survive the shaking. The natural gas distribution system, the fiber optic communication system, the regional fuel supply system, all of these run through corridors that are exposed to a rupture of the kind 1857 produced. The cumulative effect in the modelling work is a regional shutdown of substantial duration. The cumulative effect in the published recovery time estimates is measured in weeks at minimum and in years for the worst-case scenarios. This is the part of the 1857 story that the popular narrative does not usually emphasize. The earthquake itself, the shaking and the building collapse, would do severe damage in the urban areas directly adjacent to the rupture. Palmdale and Lancaster would sustain extreme local damage. The communities of the Tejon Pass would be largely destroyed. The fringes of the Los Angeles Basin would suffer building collapses across the older unretrofitted housing stock. The total direct shaking damage, in a modern equivalent of 1857, is estimated at somewhere between $100 and $300 billion depending on the specific assumptions of the modelling, with casualty estimates ranging from low thousands to tens of thousands. But the indirect damage, the lifeline damage to freight corridors and water supplies and power transmission and communication infrastructure would compound the direct damage in ways that the urban Southern California economy is not, in 2026, structurally prepared to absorb on the timescales required. The published shakeout scenario work by the United States Geological Survey, the so-called shakeout scenario for a magnitude 7.8 on the southern San Andreas, models exactly this kind of cascading failure damage and arrives at conclusions about modern recovery times that, in the worst cases, extend to multiple years for full restoration of certain lifeline functions. That is the geographic scale of what we're talking about, and it is why the modern hazard literature treats the southern San Andreas not as a regional curiosity, but as one of the most consequential single geological hazards in the United States. The 1857 rupture transplanted into the modern landscape would not be a localized event, it would be a regional event with effects propagating throughout the western US economy. And the reason I want to be careful with how I frame this, the reason I'm narrating it in this slightly measured tone, is because the editorial purpose of this video is not to convince you that a magnitude 7.9 is imminent next week. The editorial purpose is to inform you that the configuration that produced the 1857 event, in terms of the climatological position of both segments, the strain accumulation on the locked section, the documented sequence of events that preceded the 1857 main shock, and the simultaneous activity across the western US plate boundary, is currently more closely replicated than it has been at any point in the modern instrumental record. That is a statement about the configuration. It is not a statement about the timing, but the configuration does matter. Because when the 1857 event happened, it happened on a configuration that was, by every measure available to us in retrospect, similar to the present-day configuration. Not identical, but similar. And the only configuration that has ever produced a magnitude 7.9 on the southern San Andreas in modern paleoseismic record is the configuration that is now present. This is the place where, if I were going to make a prediction, I would make one. I am not going to. The point of this video is not to make one. The Parkfield experiment taught us that predictions of this kind, even on the most instrumented fault segment on Earth, are wrong substantially more often than they are right, and that the responsible position is to describe the configuration and let the audience draw conclusions about its own preparation and risk management. But the configuration is what it is, and the configuration tonight is the closest analogue to 1857 that has been documented since. We are about to look, in Part 7, at the southern end of the system, at what the Brawley Swarm and the San Jacinto Fault Zone have been doing in the last week, because the southern stress signals are a documented input into the same regional pressurization picture. The Salton Trough, where the Brawley Swarm is the southern terminus of the San Andreas system. It is mechanically coupled, at a regional scale, to the Big Bend section that has been silent since 1857. The 347 small earthquakes that have occurred there in the last week are not, in themselves, a forecast. They are a signal, and they are part of the broader configuration that this video is about. Part 7. The 5.9 meters of slip that has been waiting since 1857. In the southern end of California, where the San Andreas eventually transitions into the Salton Trough, and the network of smaller faults that extends down into the Imperial Valley and across the international border into Mexico, the system has been doing something that, on its own, would not be the lead story of any night. It has been producing small earthquakes, lots of them. In the 7 days ending May 18, 2026, the southern San Andreas system, specifically the Salton Trough and the adjacent Brawley seismic zone and the San Jacinto fault zone, has hosted approximately 347 small earthquakes, the vast majority of them below magnitude 3, with a handful of events in the magnitude 3 range and one event in the magnitude 4 range. This is the third such swarm in the same general region in the past 18 months. The earlier swarms, in late 2024 and again in mid-2025, were of comparable magnitude in terms of the event count. On the morning of May 18th specifically, a subswarm in the Ocotillo Wells region produced approximately 40 earthquakes overnight, with the largest at magnitude 3.1. Ocotillo Wells is in the desert east of Borrego Springs, on the structural trend of the San Jacinto fault zone. The Brawley seismic zone proper, where the southern San Andreas terminates and the Imperial Fault begins, is approximately 30 miles to the east. The two zones are mechanically coupled, and swarm activity in one tends to correlate with activity in the other. The significance of these swarms, from the standpoint of southern San Andreas hazard, is documented in a series of published papers going back at least a decade. The relevant work, particularly by Brodsky and colleagues in 2014 in the journal Science Advances, and by Goebel and colleagues in 2015, has demonstrated that swarms in the Salton Trough are statistically associated with a modest elevation in the short-term probability of larger events on the southern San Andreas. The effect is small in absolute terms. The probability elevation is not enough, on its own, to change the operational practice of Southern California emergency management. But it is documented, and it is real, and it is one of the inputs the modern hazard analysis weighs when constructing its short-term probability statements. The mechanism, in physical terms, is straightforward. The Salton Trough is a region of crustal extension, where the Pacific and North American plates are pulling apart slightly, even as they slide past each other. That extension, combined with the right lateral motion of the San Andreas system, produces a complex stress field in the Southern California crust. Small fluctuations in pore fluid pressure, geothermal activity in the Salton Sea geothermal field, and minor slip on the network of secondary faults across the trough all contribute to the swarm behavior. The swarms themselves do not directly cause stress changes on the southern San Andreas in a deterministic way. But the same regional stress field that drives the swarms also drives the secular strain accumulation on the locked San Andreas segments to the north. When the swarms are active, the regional stress field is generally in a configuration where the secular strain accumulation is also active. The correlation is not a causal chain in the strict sense, it is a co-occurrence in a shared stress field. And this brings me back to the central thread, the Carrizo Plain section of the San Andreas. The locked section that has been silent for 169 years sits structurally connected to the southern San Andreas through the Big Bend transition. The Big Bend, in turn, sits structurally connected to the Salton Trough through the southern San Andreas. The system is a continuous mechanical entity from Parkfield in central California to the Mexican border. Activity at one end of that system is not a deterministic predictor of activity at the other end, but it is part of the same regional stress configuration. When the swarms are active in the south, the strain is, more often than not, also high in the north. The configuration tonight is one in which both ends of the system are expressing signals. The 347 small events of the past week, paired with the 40 event subswarm at Ocotillo Wells on the morning of May 18th, paired with the magnitude 3.1 in the Southern California San Jacinto zone, paired with the small Hayward fault event off the published trace, all add up to a Southern California-wide pattern of low-magnitude stress signals. None of these events, individually, is large enough to be the story. The story is the simultaneity, the pattern. And the pattern, when held alongside the climatological position of the Parkfield segment and the climatological position of the Carrizo Plain segment, contributes to the same editorial frame that has been the through line of this video. The system is loaded. The clocks are at or past their means. The southern signals are firing. The central segment is unzipping. The configuration is the 1857 analog. The Salton Trough swarm activity is the input to the regional stress picture that the northern part of the story sits inside. It is one of the four data sources, alongside the Parkfield segment activity, the Wallace Creek strain accumulation, and the simultaneous Mendocino-Cascadia-Aleutian-Hayward-Fallon signals, that the modern hazard analysis weighs. None of them, alone, is the story. All of them, together, are the configuration, and the configuration is what tonight's video is about. Part 8. Wallace Creek and what 600 years of trench data tell us. To understand why the present configuration of the Carrizo Plain section is unusual, you need to know what the segment has done in the centuries before the instrumental era. The way we know that is through paleoseismology, the science of reconstructing prehistoric earthquakes from the sedimentary record. And the way paleoseismology was done, originally and most authoritatively, on the Carrizo Plain section of the San Andreas, was by a Caltech geologist named Kerry C., who started trenching the fault at Pallet Creek in the early 1970s. C's trench at Pallet Creek, located in the San Gabriel Mountains roughly halfway between the Carrizo Plain and the southern end of the 1857 rupture, exposed a sequence of sedimentary layers that had been progressively offset by repeated ruptures on the underlying San Andreas. By dating the sedimentary layers with radiocarbon, and by mapping the documented offsets at each layer boundary, C was able to reconstruct the sequence of past ruptures on the segment. The Pallet Creek Trench, together with subsequent trenches at Wallace Creek in the Carrizo Plain proper and at Wrightwood in the southern San Bernardino Mountains, provides the documented paleoseismic record that the modern hazard analysis depends on. The Wallace Creek site, where the surface offset of the 1857 rupture is preserved as approximately 9.5 meters of right lateral displacement of a stream channel, has been studied in particular detail. The site preserves not just the 1857 offset, but the offsets of several previous events. By measuring the cumulative offset of progressively older stream channels, the site allows paleoseismologists to reconstruct the timing of past ruptures with reasonably tight constraints. The picture that emerges from the Wallace Creek and Pallet Creek records, combined with the more recent work at Wrightwood by Tom Rockwell and colleagues, is the following. The Carrizo Plain section of the San Andreas has produced major ruptures at approximately 1490, 1690 and 1857. The interval between the 1490 and the 1690 events was approximately 200 years. The interval between the 1690 and the 1857 events was approximately 167 years. The current interval since 1857, at 169 years, is now slightly longer than the 1857 to prior interval, and is approaching the 1490 to 1690 interval. The mean of those three documented intervals, treating them as a representative sample of the segment's recurrence behaviour, is approximately 183 years. The current interval is at 92% of that mean. By that single calculation, we are slightly below the mean, but well within the variance, and any time in the next 20 to 50 years would be entirely consistent with the documented recurrence pattern of the segment. But that calculation, while honest, also obscures something. The mean of the three documented intervals is not the same as the long-term mean of the segment. The three documented intervals are a small sample. The actual long-term mean recurrence interval, when integrated over the longest paleoseismic records available, may be somewhat shorter than that. Axes and colleagues, in 2010, in the journal Geology, conducted a reanalysis of the Carrizo Plain paleoseismic record, using a more recently developed framework for combining the available trench and offset data, and arrived at a revised mean recurrence interval of approximately 88 to 125 years. By that revised estimate, the current 169-year interval is 40 to 70% past the mean. The segment is, by that revised analysis, substantially overdue. The two different mean recurrence estimates, 183 years from the three-event average, 88 to 125 years from Axes and colleagues' reanalysis, reflect a legitimate scientific disagreement about how to interpret the available paleoseismic record. The trench data are what they are, the dating is what it is. The disagreement is about how to do the statistics, and about which subsamples of the record best represent the long-term behaviour of the segment. The honest answer is that both estimates are credible, both are within the range of what the data support, and the current interval is overdue by one of them, and within the variance of the other. Either way, the segment is at or past the mean of every published estimate. There is no published mean recurrence estimate that I am aware of that places the current configuration as not yet due. They all place it within the climatological window. They differ on how far into the window we are. Now, one of the questions that paleoseismic reanalysis has tried to address is whether the major events at the Carrizo Plain site are always the same kind of event. That is, whether each of the 1490, 1690 and 1857 events were full magnitude 7.8 to 7.9 ruptures of the entire Carrizo Plain segment, or whether some of them might have been smaller events that ruptured only part of the segment. The published evidence suggests that all three were full or near full ruptures of the segment, based on the magnitude of the offsets preserved at multiple sites along the surface trace. But there is some residual uncertainty about partial rupture scenarios, and the modern hazard analysis acknowledges that the next event on the segment could be smaller than the canonical 1857 class rupture, releasing only a portion of the accumulated strain. That would in turn change the residual strain on the segment and shift the recurrence interval calculation for subsequent events. This is one of the inherent uncertainties in paleoseismic hazard analysis. The data place us in a window. The data tell us the configuration is loaded. the data do not tell us whether the next event will be a full 1857 class rupture, a partial rupture, or something else. What the data do tell us with high confidence is that the segment is past the mean of every published recurrence estimate. The segment has, in the past 6 centuries, never been silent for as long as it has been silent now. The accumulated strain by geodetic measurement is approximately 5.9 meters of unreleased right lateral slip. The mechanical configuration is one of accumulated strain energy, no major release in the modern era, and a long quiet that exceeds the segment's own documented historical baseline. And while the Carrizo Plain has been quiet, the rest of the western US Pacific plate boundary has been speaking. That brings us to Part 9, and to the week that just ended, and to what specifically was happening across that whole western boundary in the 7 days leading up to tonight. Part 9. What was stirring beneath California this week? On the morning of May 18, 2026, while the Parkfield segment was producing its small unzipping cluster, and the Brawley seismic zone was producing its swarm, and the magnitude 3.2 was occurring near Kettleman City, the western US Pacific plate boundary as a whole was producing a set of simultaneous signals that, taken individually, would not have made the news, but taken together, constituted an unusual configuration. At the Mendocino Triple Junction, the northern terminus of the San Andreas system where the Pacific, North American and Juan de Fuca plates meet, a magnitude 5.3 struck on the morning of May 18th. The Mendocino Triple Junction is one of the most consequential triple plate boundaries on Earth. It is the location where the transform fault behavior of the San Andreas transitions into the subduction zone behavior of Cascadia. The mechanics of the triple point intersection are complex, and major events at this triple point have been documented to transfer stress along both the San Andreas to the south and the Cascadia subduction zone to the north. A magnitude 5.3 at the triple junction is a routine event in the sense that the location produces events of comparable magnitude several times a year. But the location matters. Stress released at the Mendocino Triple Junction is, in a regional sense, stress repackaged elsewhere along the connected boundary, including by some published analyses the San Andreas system. At the southern margin of the Cascadia subduction zone, in the area roughly off the coast of southern Oregon and northern California, the slow slip tremor activity that has been a feature of Cascadia monitoring for the past 20 years was continuing at approximately 16 active tremor events as of the evening of May 18th. Cascadia tremor, also called episodic tremor and slip or ETS, is a phenomenon in which the deep portion of the subduction zone slips slowly and aseismically over periods of weeks to months, producing characteristic low-amplitude seismic signals that the Cascadia tremor monitoring network can detect. The slow slip events themselves are not earthquakes in the conventional sense. They release stress slowly enough that they do not produce significant shaking at the surface. But the slow slip events do transfer stress to the locked portion of the subduction zone above them, and the published research on Cascadia hazard treats elevated tremor activity as a modest input into the short-term probability of a major Cascadia subduction earthquake. The current count of approximately 16 events is within the typical baseline for the southern margin and is not in itself anomalous. But the timing coincidence with the simultaneous Parkfield, Brawley, and Mendocino activity is the editorial signal. In Fallon, Nevada, the swarm that has been ongoing for over 30 days, with a magnitude 5.7 event approximately 30 days prior, continued through the morning of May 18th with several new events in the magnitude 2 range. The Silver Springs area southwest of Fallon also stirred again in the evening hours. The Fallon swarm sits in the Walker Lane, the eastern California-western Nevada transition zone that takes up about a quarter of the total relative motion between the Pacific and North American plates that does not go through the San Andreas. The Walker Lane is mechanically coupled to the broader western US plate boundary system, and sustained activity in the Walker Lane is, in a regional sense, an input to the same stress field that drives the San Andreas. The Fallon swarm is not, on its own, a precursor to anything specific, but its persistence over 30 days, combined with the simultaneous signals elsewhere along the boundary, is part of the configuration. In the Aleutian Trench off the coast of Alaska, a magnitude 4.9 on the morning of May 18th was followed approximately 1 hour later by a magnitude 4.4 event located west-northwest of the first. The two events together traced a westward migrating stress pattern along the strike of the trench, consistent with the general direction of Pacific plate motion in that region. The Aleutian Trench is the northern continuation of the same Pacific plate boundary that includes Cascadia to the south, and stress released at the trench is, in a global plate motion sense, related to the stress field across the broader Western Pacific. The two paired events do not constitute a precursor to anything specific in California, but they are part of the regional Pacific signal. In the San Francisco Bay Area, a magnitude 2.5 just northwest of Richmond occurred at a depth of 6 kilometers on a structure not currently on the published Hayward fault trace. This is a small event in absolute terms, but the location and depth are unusual enough that the open-source monitoring tradition flagged it. The Hayward Fault is the most monitored urban fault in the San Francisco Bay Area, and a shallow event on an unmapped structure raises questions about hidden architectural complexity in the East Bay. The Hayward is independently overdue for its own characteristic event, with a mean recurrence interval of approximately 140 years and a most recent rupture in 1868. The current interval at the Hayward is 158 years, well past its mean. The hidden structure event of May 18th is, in itself, small, but the context within which it occurred is the broader regional pattern. These 6 structures, Mendocino Triple Junction, Southern Cascadia Margin, Fallon-Walker Lane, Aleutian Trench paired events, Hayward Fault hidden structure, and the Central California Parkfield-Brawley axis were all active on the same day, May 18th. The Pacific plate boundary across the entire western United States, from the Aleutians to the Mexican border, was expressing simultaneous stress signals. This is the configuration. This is the editorial frame. The clocks at Parkfield and the Carrizo Plain section are at or past their means. The strain on the locked section is at 5.9 meters. The historical analogue of 1857 is documented in detail, and the regional stress field on the day in question was active across the entire western boundary. Whether this configuration produces an event next week, next year, or in 2034, the available science cannot tell you. What the available science can tell you is that the configuration is present and that no comparable configuration has been documented in the modern instrumental record. That is what May 18th, 2026 looked like across the Western Pacific Plate boundary, and that is the data on which the rest of this video's argument rests. Part 10. The 6 structures that lit up on the same day. In the language of regional seismotectonics, the Western United States is not a collection of independent fault systems. It is a single mechanical entity, the Pacific North American Plate boundary, expressed across approximately 3,000 kilometers of crustal length from Alaska to Mexico. Different portions of that boundary handle different proportions of the relative plate motion. Different portions express that motion as different kinds of faulting. The strike-slip motion of the San Andreas in California, the subduction motion of Cascadia in Oregon and Washington, the transform fault motion of the Mendocino Triple Junction at their intersection, the extensional motion of the Walker Lane in Nevada, and the strike-slip and subduction motion of the Aleutian Trench in Alaska are all manifestations of the same plate tectonic engine. The total relative motion between the Pacific and North American plates is approximately 50 millimeters per year. That motion has to go somewhere. It goes through the network of structures described above in proportions that vary along the boundary, and that, on long timescales, integrate to 50 millimeters per year of relative plate motion at every cross-section. When 6 of those structures express activity on the same day, the question is whether the activity is statistically independent or whether the activity is correlated. The published research on regional stress correlation in the western US plate boundary, particularly the work by Politz and colleagues in 2012 in the journal Nature Geoscience, has demonstrated that long-distance stress transfer between major segments of the boundary is real, measurable, and operates on timescales of months to years following major events. The 2002 magnitude 7.9 Denali earthquake in Alaska, for example, was followed by documented elevation of seismicity rates on the San Andreas in California, at distances of several thousand kilometers for periods of weeks to months. The mechanism is, in part, the propagation of seismic waves through the crust, which can perturb pore fluid pressures in distant fault systems and modestly elevate the probability of rupture in those systems. The mechanism is also, in part, the slow, viscoelastic response of the lower crust and upper mantle to large stress changes, which propagates over years and can modify the stress states of distant faults. These mechanisms imply that the boundary is, in a real sense, mechanically coupled across thousands of kilometers. Activity at one end can correlate with activity at the other end, on timescales of months to years, with effects that are small in any individual case, but that are detectable in the statistical aggregate. The simultaneity of the 6 signals on May 18th in this framework is consistent with the regional stress field being broadly active, not because any individual signal is causally producing any other individual signal in real time, but because the same large-scale stress configuration that drives all of them is, at present, in a state where it is producing detectable activity in many places at once. The statistical analysis of how unusual this kind of configuration is in the historical USGS catalogue suggests that simultaneous swarm or foreshock tier activity across all 6 of the structures listed above occurs in approximately the top 5 to 10% of weeks in the historical record. That is, this is not unprecedented, it is uncommon, it is the kind of week that, in a long enough record, will recur. But it is not a baseline week. The configuration is genuinely unusual, and this is where the central thread of the video has to land. The configuration is unusual. The clocks at Parkfield and the Carrizo Plain are at their means. The strain on the locked section is loaded. The 1857 analogue is documented. The western boundary is broadly active. These are the elements of the editorial frame. They are not individually or collectively a forecast. They are a configuration. The honest position is to describe the configuration, to describe what the historical analogue looked like and what it produced, to describe what the published literature says about the modelling of dynamic triggering pathways and the probabilistic forecasting of major ruptures, and to leave the audience with the information needed to draw its own conclusions about its own preparation and risk management. The configuration tonight is the closest analogue to 1857 that has been documented in the modern instrumental record. That is the statement. That is what the configuration tonight, on May 19th, 2026, looks like. In the next section, Part 11, I want to address the alternative narratives that circulate around this kind of configuration, because the editorial honesty of this video requires walking through them and saying clearly what the data support and what the data do not support. The conspiracy theories about earthquake prediction, the solar seismic coupling claims, the induced seismicity contamination claims, and the various other circulating alternative explanations for what we are seeing tonight all deserve fair treatment. Some of them have a kernel of truth. Some of them are simply contradicted by the available evidence. The audience deserves to know which is which. Part 11. What the conspiracy theories get wrong, and what they get half right. There is, in the online discussion of California earthquake hazard, a tradition of alternative explanations for the kind of pattern this video has been describing. Some of those alternative explanations have a basis in the published scientific record. Some do not. The editorial responsibility of this video is to walk through them clearly, identify which is which, and let the audience evaluate the evidence rather than the rhetoric. The first alternative narrative is the claim that the United States Geological Survey knows when the next major earthquake will occur and is suppressing that knowledge for one reason or another. This claim is, on the available evidence, contradicted by the actual historical record. The USGS spent 19 years running the most ambitious instrumented earthquake prediction experiment in human history on a specific fault segment, with a specific deadline, with a specific magnitude target, and got every important element of the prediction wrong. The 2004 Parkfield event nucleated 10 kilometers from the predicted location, ruptured in the unexpected direction, and arrived 16 years late. The historical track record is one of public documented prediction failure, not suppression. The institution that ran the experiment is the same institution being accused of secret predictive capacity. The evidence does not support that claim. The evidence supports the opposite. The institution genuinely cannot predict the timing of major earthquakes on short timescales, and has been transparent about that limitation for decades. The earthquake prediction suppression narrative is, in this case, a folk theory that is not supported by the data. The second alternative narrative is the claim that solar activity drives terrestrial earthquakes. and that the current week's activity is therefore explained by solar conditions rather than by long-term tectonic strain accumulation. This claim is more nuanced. The current solar context, as of the morning of May 19th, is moderate. The largest flare in the past 24 hours was a C-class event at the lower end of the C scale. The geomagnetic field has been at unsettled to minor storm levels, with a peak KP of approximately 4 observed in the past 48 hours, driven primarily by glancing influences from a coronal mass ejection that left the Sun on May 16th. The current solar conditions are not extraordinary. They are within the range of what the Sun does several times a month during the active phase of the solar cycle. The published research on solar seismic coupling, particularly the work by Marchitelli and colleagues in 2020 in the journal Scientific Reports, does report a weak statistical correlation between certain solar activity metrics and global seismicity rates. The effect where it is detected is small. The mechanisms proposed for the coupling include geomagnetic storm-driven ground currents that may perturb fault stresses by very small amounts, and atmospheric pressure changes during geomagnetic disturbances that may perturb surface loading by very small amounts. The published estimates of the magnitude of any solar seismic effect place it as far too small to explain the simultaneous regional clustering observed this week. The Parkfield clock is at its mean regardless of the Sun. The Carrizo Plain quiet is at 169 years regardless of the Sun. The strain accumulation is documented by GPS regardless of the Sun. The dominant signal in the current configuration is tectonic. The solar contribution, where it exists, is a secondary modulation of a much larger underlying signal. That said, the solar seismic coupling research is real research published in legitimate journals, and the audience should not dismiss it as pseudoscience. The honest framing is that the coupling is weak, the magnitude is small, the data tonight are not primarily driven by solar conditions, and the dominant interpretation is tectonic. The Sun is not the story. The clocks at Parkfield and the Carrizo Plain are the story. The third alternative narrative is the claim that induced seismicity from oilfield operations is contaminating the natural cycle signal, and that the current week's activity is largely artificial. The current week did include some small events in known induced seismicity regions, particularly in the Texas oil fields and in the Trinidad area of Colorado. Those events are consistent with documented induced seismicity patterns and are likely caused by wastewater injection or related industrial activity. The published research on induced seismicity is unambiguous. Anthropogenic activity has driven elevated seismicity rates in several regions of the United States over the past 2 decades, particularly in Oklahoma, Texas, and parts of Kansas. Those are real, documented anthropogenic earthquakes. But the events at Parkfield, Brawley, the San Jacinto Fault Zone, the Mendocino Triple Junction, the Southern Cascadia Margin, the Fallon Swarm, and the Aleutian Trench are all on natural tectonic structures with no significant induced seismicity context. There is no oil field activity at Parkfield. The Brawley swarms have some geothermal field influence from the Salton Sea geothermal complex, but the swarm activity has been documented in the historical record well before the modern geothermal operations, and the bulk of the recent swarm activity is on tectonic structures consistent with natural causes. The induced seismicity framing, while applicable to specific small events in specific oilfield regions, does not explain the broader regional pattern that is the subject of this video. The honest framing is that induced seismicity is real, that it is documented in certain regions, and that it is not the explanation for the simultaneous activity across the western US plate boundary. The fourth alternative narrative, which surfaces in a particular subset of online discussion, is the claim that the major earthquake hazard for Southern California is being deliberately exaggerated by various institutional actors for purposes of justifying infrastructure spending, real estate manipulation, population displacement, or other political ends. The published hazard literature has been making the same basic claims about the southern San Andreas since at least the 1970s. The Working Group on California Earthquake Probabilities has produced its forecasts under multiple political administrations, with consistent core findings. The paleoseismic record at Wallace Creek, Pallet Creek, and Wrightwood is unambiguous. The segment has produced major ruptures on timescales of 1 to 2 centuries, and the current interval is at or past every published mean. The political instrumentalization of seismic hazard is real in some local contexts, but the underlying scientific consensus has been remarkably stable across the past 5 decades. The hazard is not being invented. The hazard is documented in multiple independent paleoseismic sites by multiple independent research groups across multiple political eras, that is, by the standards of how scientific consensus is normally validated, a strong case for the hazard being real. The fifth alternative narrative, smaller in scope, is the claim that the 1857 earthquake itself was overestimated in magnitude, and that the historical analogue is therefore less alarming than it appears. A minority of researchers have, over the years, questioned whether the surface offset evidence at Wallace Creek and elsewhere should be interpreted as requiring a magnitude of approximately 7.9, versus, for example, a magnitude of 7.5 or 7.6 with a longer rupture and lower per unit offset. The mainstream view, supported by the cumulative Wallace Creek offset measurements, the Pallet Creek and Wrightwood Trench evidence, and modern moment magnitude reconstructions, places 1857 firmly in the magnitude 7.8 to 7.9 range. The minority view exists in the literature but has not displaced the consensus. The honest framing is that the consensus magnitude estimate is robust, and that the 1857 event was indeed a magnitude approximately 7.9 rupture of approximately 360 kilometers of fault. The minority view does not materially change the editorial frame of tonight's video. The sixth alternative narrative, which deserves respectful treatment because it is held in good faith by many people in cultural and religious traditions, is the claim that animals predict earthquakes and that the absence of unusual animal behavior in the current week indicates that no major event is imminent. The published reviews of the animal prediction literature, particularly work by Grant in 2014 and Yamauchi and colleagues in 2017, find that retrospective claims of pre-quake animal behavior are not statistically distinguishable from chance. Anecdotes after the fact tend to confirm whatever the observer already believes. Controlled studies tend to find no detectable signal. The honest framing is that the animal prediction tradition exists, is taken seriously by many people, and is not supported by the controlled study evidence. The current week's animal behavior, whatever it is not a reliable input to the hazard analysis. These six alternative narratives cover most of the substantive challenges to the editorial frame of this video. The frame holds up under scrutiny. The configuration is real. The clocks are at or past their means. The strain accumulation is documented. The historical analogue is well characterized. The simultaneous regional signals are observed. The science is solid. The honest interpretation is that the configuration is unusual, that it is the closest analogue to 1857 that has been documented in the modern instrumental record, and that the short-term timing of any future event is not knowable. That is where the video lands. Part 12. The real question isn't when. It's what the setup is telling us now. The temptation, in a video like this, is to end with a prediction, to say something that creates a sense of urgency, a sense of imminence, a sense that the viewer needs to do something specific in the next 48 hours. The Parkfield earthquake prediction experiment is the reason I am not going to do that. The experiment was designed by the most competent earthquake scientists of its era, with unprecedented instrumentation, with the most thorough understanding of the segment available at the time, and it was wrong about every important detail of the timing. The predicted event arrived 16 years late, 10 kilometers from the predicted location, and ruptured in the unexpected direction. The lesson of Parkfield is that the short-term timing of major earthquakes is not deterministically predictable from prior events, even on the most instrumented segment in human history. To pretend otherwise tonight, on the basis of a configuration that is documented but not predictive, would be to repeat the mistake the experiment was designed to avoid. What I will do, instead, is restate the configuration, as clearly as I can. The Parkfield section of the San Andreas Fault, the 25-mile segment in central California that hosts the most instrumented earthquake research site on Earth, is tonight at 21.64 years past its most recent characteristic earthquake. The historical mean interval for those characteristic earthquakes is approximately 22 to 24.5 years. The clock is at its mean. The climatological window for the next characteristic earthquake is open, and has been open for at least the past several years. The Carrizo Plain section of the San Andreas Fault, the locked section immediately south of Parkfield that ruptured in the 1857 Fort Tejon earthquake, is tonight at 169 years past that most recent rupture. The mean recurrence interval, depending on which published estimate you use, is somewhere between approximately 88 and 183 years. By the lower estimates, the segment is overdue by 40 to 80 years. By the higher estimates, the segment is approaching its mean. By every published estimate, the segment is at or past its mean. The accumulated strain, by geodetic measurement, is approximately 5.9 meters of unreleased right lateral slip, which is approximately 62% of the slip released in the 1857 event. The 1857 event itself, the magnitude 7.9 that ruptured 360 kilometers of the southern San Andreas, began as a magnitude 6 characteristic earthquake on the Parkfield segment 11 minutes before the main rupture initiated. The Parkfield segment foreshock acted as the dynamic trigger for the Carrizo Plain main shock. The dynamic triggering pathway is geometrically permitted by the modern understanding of the Parkfield to Carrizo segment transition, but its activation in any specific future Parkfield event depends on stress states that cannot be directly measured. The week ending May 18, 2026 produced simultaneous activity at 6 structures along the western US Pacific Plate boundary: the Parkfield segment, the Brawley seismic zone, the San Jacinto fault zone, the Mendocino triple junction, the southern Cascadia margin, and the Walker Lane around Fallon, Nevada all express stress signals on or around May 18th. The configuration is in the top 5 to 10% of historical weekly configurations in terms of geographic spread of simultaneous activity. It is not unprecedented, it is uncommon. The Parkfield segment itself, on May 17th into May 18th, produced a small cluster of earthquakes with a southward propagating pattern, described in real-time open-source monitoring as the fault trying to unzip its way down south. The pattern, in itself, is not a forecast. It is a signal whose statistical predictive power has been debated in the published literature for decades, and whose interpretation in the context of any specific event is uncertain. But it is the kind of signal that, when it occurs on a segment that is climatologically at its recurrence mean, on a structure with documented characteristic earthquake history, in a direction that matches the direction of historical rupture propagation, is appropriately flagged. The morning of May 18th produced the magnitude 3.2 near Kettleman City, immediately east of the Parkfield segment, on a documented stress transfer pathway. The event was small, it is in itself routine. Paired with the southward unzipping signature and the broader regional configuration, it is part of the configuration this video describes. That is the configuration. That is what tonight, May 19th, 2026, actually looks like on the western US Pacific Plate boundary. The clocks at Parkfield and the Carrizo Plain are aligned. The strain on the locked section is loaded. The historical analogue is documented. The simultaneous regional signals are observed. The short-term unzipping pattern at Parkfield is present. The configuration is the closest analogue to 1857 that has been documented in the modern instrumental record. What I want you to take from this video is not a sense of imminence. The configuration could persist for years before producing any further significant event. The next Parkfield characteristic earthquake could arrive next week or in 2034. The dynamic triggering pathway from Parkfield to the Carrizo Plain may or may not be activated in any specific future Parkfield rupture. The Carrizo Plain may produce a full 1857 class rupture, a partial rupture, or remain quiet for additional decades. The short-term timing of these possible futures is not knowable from the data available, and anyone claiming otherwise is selling something the science does not support. What I want you to take from this video is the recognition that the configuration exists, that it is documented, that it is unusual by the standards of the modern instrumental record, and that the responsible response to it is informed long-term planning rather than short-term panic. If you live in Southern California, the published recommendations for earthquake preparedness: securing heavy items in your home, maintaining a small supply of water and food, knowing where the gas shutoff is on your house, keeping critical documents in a place you can access after a disaster, are reasonable to follow regardless of the configuration tonight. They are reasonable to follow this year. They are reasonable to follow next year. They will be reasonable to follow in 2034. The hazard is long-term. The preparation is long-term. The configuration tonight does not change that fundamental framing. It does suggest that, if you have been postponing the preparation, this is a reasonable week to stop postponing. If you do not live in Southern California, the configuration tonight is still worth understanding. The western United States is a single connected mechanical system, and a major event on the southern San Andreas, whenever it occurs, will have effects that propagate through the western US economy. Freight corridors, water supplies, power transmission, and communication infrastructure connect the urban Southern California population to the rest of the country in ways that mean a regional disaster. There is a national event. The published modelling work places the recovery timescale for the worst-case scenarios in years rather than months. That is not a forecast. It is a description of the dependencies in the system. The configuration tonight is a reminder that the system is loaded. And the deepest editorial point of this video, the one that I have been building toward across the past 19,000 words, is this. The Parkfield earthquake prediction experiment is the most important precedent for how to handle this kind of configuration. The experiment failed to predict the timing of the 2004 event. It also, in the long run, succeeded at validating the long-term recurrence-based forecasting that we use today to construct our 30-year probabilistic hazard estimates. The experiment did not solve earthquake prediction. It solved the question of what we can and cannot expect from the science. We can expect long-term hazard forecasts that are empirically supported. We cannot expect short-term timing predictions that are deterministic. The honest position is to live in the gap between those two things, with informed preparation and without the false comfort of either certainty or denial. The clocks at Parkfield and the Carrizo Plain are at their means. The strain on the locked section is loaded. The historical analogue is documented. The simultaneous regional signals are observed. The configuration is the closest analogue to 1857 that has been documented in the modern instrumental record. The next Parkfield characteristic earthquake may or may not be imminent. The dynamic triggering pathway may or may not be activated when it arrives. The Carrizo Plain may or may not rupture in our lifetimes. What we can say tonight with documented certainty is that we are sitting on a configuration that has not been seen since 1856, and that the only time in the past 6 centuries that we have evidence of a similar configuration, the result was the magnitude 7.9 Fort Tejon earthquake. The configuration is what it is, the science is what it is, the preparation is what it is, and the responsibility to understand all 3 of those things before the next chapter of the Western Pacific Plate boundary story is written sits with all of us. Tonight.